Dear students, welcome back to this last assignment of this course. So as usual, the first 6 problems in this assignment should be done in your live sessions. We will start doing from the 7th problem here. Okay, so in the 7th problem, what it is saying is that in the lectures we have computed the derivative of Laplace transform. Okay, now in this exercise problem we need to compute the integral of Laplace transform. So we have to show that the integral of Laplace transform is Laplace transform of f. So you have seen that the derivative of Laplace transform is is the Laplace transform of the function multiplied by polynomials. In this case, the integral is Laplace transform of the function, which is again multiplied by polynomials of negative degree. Okay, so to do that, what we do is the first we start with g of x to be f of x over x. From this we get that f of x is xgx. Okay, so now what is Laplace transform of f? Laplace transform of f is nothing but Laplace transform of x gx, right? But we know from the lectures that the derivative of Laplace transform is nothing but multiplication by polynomial, which is the case here. So x is multiplied, so this is minus the derivative of Laplace transform of g. Okay, so this is what we have from this formula. Now we need to compute the integral. Okay, so integral of p to infinity will give you integral of p to infinity. So this is integral of the derivative. So that's going to give you integral of derivative is Laplace transform of g, in this case p. So here this you can make this s, and make this s, so here as well. Okay, so LGP minus the value of Laplace transform at infinity. So let's take it as LG of s, this one. So now we have already seen, we have already given an exercise number 3, where we have shown that the Laplace transform goes to 0 as p goes to infinity. Okay, this is under the assumption that f is of exponential order, because that is because of this course, due to the level of the course we are giving this assumption. Otherwise this result is valid anyway, and this result is also valid for g, for this function g that you have defined here. That result is valid, that the Laplace transform is vanishing as it goes to infinity. So this is just Laplace transform of g of p. Okay, so this is the part. This is the part we need to prove, which is we have proved this. Now let's do 7a. So what is 7a? It's asking us to compute the Laplace transform of e power x sine ax over x, and it's asking us to so we have to find the Laplace transform using this result that we proved here. So if we have to use this result, so in this case the numerator, so there is a denominator anyway x, right? So the numerator has to be, so let's call the numerator as f. Okay, so let's call this as your f of x. So we know Laplacian of f of x is equal to integral of something, so it's integral of p times infinity Laplace transform of exponential of x sine, so now sine ax of s ds. This is by the formula that we have just derived. Okay, so now what is the Laplace transform of e power x sine ax? This is precisely the first shifting theorem, right? So that tells you that this is equal to integral p to infinity. So we know that the Laplace transform of sine is a by sine ax is a by p square plus a square, right? Now we have a translation by so we have multiplication by exponential of x, which means it's going to translate. So what we are going to have is precisely a times let's call it a times, so in this case it's s, right? So s minus 1 whole square plus a square. Okay, so that's it, and this is by the first shifting theorem. Okay, so for the first shifting theorem we have this, and this is ds. Now if you integrate this, okay, if you integrate this with infinity and so on, so what you get is pi by 2 minus tan inverse or arctan of p minus 1 over a. Okay, so that's 7. That's what this is. So Laplace transform of that is computed. Now let's do 7b. Okay, so for 7b, we have to compute Laplace transform of sin x cos hyperbolic x divided by x, right? So your numerator is sin x cos x, sin x cos hyperbolic x. So what we need to use is this information that cos hyperbolic x has this is nothing but e power x e power minus x by 2. Okay, so this is like we have the Euler's formula and complex numbers and so on. This is like that. So the hyperbolic functions are the exponential plus exponential of minus index over 2. Okay, so if we use this, so what is this Laplace transform? By this result that we have, this is equal to integral p times Laplace transform of sin x cos hyperbolic x, okay, of s ds. Okay, so this is equal to this, and this is equal to what you have here, right? So if you multiply sine here, what you do is you multiply sine here, which is precisely e power x sin x over 2 e power minus sin x over 2, right? And that, so Laplace transform by the linearity is precisely integral p to infinity Laplace transform of e power x sin x over 2. So let's bring the over 2 outside. That's fine. So that's going to give you it's a, so it's 1 s minus 1 whole square plus 1 plus 1 times s plus 1 whole square plus 1. Okay, integral of that, and that is precisely 1 by 2. If you integrate it, the first term is going to give you pi by 2 minus tan inverse of s minus 1. Okay, minus plus pi by 2 minus tan inverse of s plus 1. Okay, so that's going to be half pi by 2 becomes pi minus tan inverse of s minus 1 minus tan inverse of s plus 1. Okay, so that's the result. That's the Laplace transform of this, whatever we wanted to find. So we have done both 7a and 7b using this property. Okay, now let's try doing problem number 8. Okay, so in problem number 8a, let's do 8a. We need to find the inverse Laplace transform, and as you can remember, we have not given a precise definition of inverse Laplace transform in the course, because this course is it's beyond the level of this course. So that definition is not, the precise definition is not being given. So the way we are computing inverse Laplace transform is for simple functions where we can we can kind of retrace the steps back. Okay, so we are just going to find the inverse Laplace transform by finding the functions whose transform is this. Okay, so in some sense, some kind of reverse chronological order. Okay, so what we need to find is we need to find f such that L of f is log of p square plus 1 by p plus 1 whole square. Okay, so we need to find f such that this happens. So since we don't have a direct formula for inverse Laplace transform, if we knew, we could have just taken the inverse Laplace transform of whatever is here and then compute it. We are not going to do that. We are just going to see whether we can write this as Laplace transform of some, write the right hand side here as Laplace transform of some function. So for that, let's use some properties of Laplace transform. So if we differentiate both sides, what you get is the derivative of the Laplace transform is the derivative of whatever is here, which is p plus 1 whole square, p square plus 1, and derivative of this, so that's p plus 1 whole square 2p minus p square plus 1 to p plus 1 and derivative which is 1, okay, and divided by the square of the denominator, which is p plus 1 power 4. Okay, so now what you do is that this cancels off with some 2 here. Okay, so now what you get is and this square here will cancel with this square here, so what you get is 2p square plus 1 minus, in this case this cancels with this and one of this cancels with one of this, so what you get is 2 by p plus 1. Okay, so now what is the function whose Laplace transform is this? So you can see that this by definition is Laplace, and this by the definition of Laplace transform is nothing but cos x minus 2, and this one is by definition the Laplace transform of exponential of minus x. Okay, now by the linearity of the Laplace transform, you can write this as Laplace transform of 2 times cos x e power minus x. Okay, but what is that you know about right? What is that we know about d by dp of LF? It is nothing but minus times Laplace transform of x fx. So, and we have just shown that this is same as this, which means this is equal to this. So what we have is that x fx is 2 times cos x minus e power minus x. So fx is 2 times cos x minus e power minus x by x. Okay, so that completes problem 8a. Okay, now so we have computed the f for which, so we have actually computed the f for which LF is the given function. Now we need to do similar thing for this 8b. So let's do 8b. In 8b we need to find f such that the Laplace transform of f is 1 minus exponential of minus 2p 1 minus 3 times exponential of minus 2p over p square. Okay, so if we need to find this, so you can just simplify this. Okay, so this becomes 1 over p square minus 4 times exponential of minus 2p by p square plus 3 times exponential of minus 4p by p square. Okay, now individually we know what is the Laplace transform of this. So each of them, so the first one is 1 over p square, so it's a Laplace transform of the function x minus 4. It is again we have to use the second shifting theorem because it's multiplied by exponential 1 over p square. So in this case it is 4 times x minus 2, the Heaviside function of hx minus 2, plus 3 times x minus 4 and the Heaviside function of x minus 4. Okay, so by linearity, we have I missed something here. Let's erase this. So what we have is minus L of this plus L of this, right? That's what we have. So that gives us if we by linearity, because there is an L here, L everywhere here, so f of x is equal to x minus 4 times x minus 2 h of x minus 2 plus 3 times x minus 4 h of x minus 4. Okay, so here again we have used the second shifting theorem to write down this as translations. Okay, and in this case this is also valid for all p positive. So that is 8b. So with this we have solved 8a and 8b both. So this is your final answer in terms of Heaviside function. Okay, now let's look at the next problem. It's the 9th problem, 9a. So 9a, so let me start 9a from here, let's say. Okay, 9a. So 9a is we need to use the Laplace transform to solve the initial value problem. Okay, so in this case the initial value problem, so the right hand side whatever is given here, this is, let's say, your f of x. Okay, so f of x is given as some okay, so basically it is some scaling okay, and then we have this we have this 0. So this is the point, let's say pi. Okay, so and this is your function f of x that is given to you. Okay, let's say, okay, so this is 8 sin x. So this is the f of x that is given to you, that is this entire thing what we have drawn here. Okay, so now so we need to use Laplace transform to find this function. So let's apply Laplace transform. So you apply Laplace transform both sides. So you apply Laplace transform both sides here. So L of y by linearity, L of y double prime will be p square, right? P square L of y minus p times y of 0 minus y prime of 0. So this one term gives you these three terms here, plus 9 times Laplace transform of y is equal to Laplace transform of f, right? So y prime, this is equal to 4 is given, this is equal to 0 is given, so this basically becomes p square plus 9 Laplace transform of y is equal to Laplace transform of f. So the differential equation has now become an algebraic equation, right? So from here, what you actually get is that the Laplace transform of y, because y is the unknown, which means Laplace transform of y is the unknown in this algebraic equation. This is nothing but Laplace transform of f divided by p square plus 9. Okay, so now finally boils down to finding what is Laplace transform of f. So what is Laplace transform of f? So what is f? F is, as you see, 8 sin x up to 0 pi and 0 after this, which is what we have drawn here, which is this is your f of x. So this function can be written, as you can see, is written as 8 sin x hx. Hx is the Heaviside function. In the positive real line, it's going to be 1. So this is a function which is 8 sin x in the entire positive line, right? Whereas what you want is it's 8 sin x only up to pi, and after that it becomes 0. Okay, so what you should do is that you should subtract 8 sin x after pi. So you subtract 8 sin x after pi, x minus pi. So h of x minus pi, right, h of x minus pi sin x. H of x minus pi is something which is 1 after pi, so it cancels with 8 sin x, so it makes it 0 in the interval pi comma infinity. So this is your fx. Okay, and this you can simplify little bit to fit it into our Laplace transform formula, that this is 8 sin x can be written as plus x minus pi h x minus pi, right? Because sin x minus pi is minus sin x. Okay, so this is your fx. If this is your fx, what is your LF? That is Laplace transform of x, right? So we need to find that, which is precisely 8 times, so sin x of hx, right? So this is we need to use the second shifting theorem like we did before. So second shifting theorem is trying to tell you this is exponential of minus okay, in this case it's actually 0, so exponential 0, so it's just 1 over sine of x, which is precisely p square plus 1, right? So it's 8 p square plus 1, the first term. The second term is 8 exponential of plus pi, so there is a minus pi, x minus pi, right? So yeah, x minus pi divided by p square plus 1. This is 8 times p square plus 1 plus exponential of minus pi. This is the Laplace transform of f. No, something I missed, no? Yeah, I missed something here. I should correct this, right? So p square plus 9 ly is fine. This is 0, so it's minus 4. So it's minus 4 times L of f. and so that will make this is Ly plus 4, right? Okay, so now what is Ly? It's equal to 4 by p square plus 9 plus Lf, which is this, so 8 p square plus 1 and p square plus 9 times 1 plus exponential of minus pi. Okay, now this is Ly, so now we have to use partial fractions. So if you use partial fractions, you get this will remain as such. In fact, this you can write it as Laplace transform of 4 by 3 sine 3x, right? And here, if you use partial fractions, you are going to get 1 plus exponential minus p, okay, 8 of that. If you use partial fractions, then you can write it as p square plus 1 minus 1 by p square plus 9. Okay, now this is precisely Laplace transform of 4 by 3 sine x, and then 1 times this entire thing. Okay, that's going to give you Laplace transform of sine x minus 1 by 3 Laplace transform of sine 3x. Okay, and then by the second shifting theorem, the product of this with that, which is going to give you plus h of x minus pi sine x minus, so this is Laplace transform of this entire thing. So Laplace transform of sine x minus pi minus 1 by 3 sine 3 x minus pi, that. Okay, so this is what you get. So if you use linearity of the Laplace transform, what you get is y of x is 4 by 3 sine x. Okay, so there is a 4 by 3, sorry, so there is a 4 by 3 sine x here, and there is a minus 1 by 3 sine x here. So 4 minus 1, 3 by 3 is 1, so it's just, oh, not here, sorry, yeah, this I made a mistake, right? So that I didn't write it properly. This should be, this is sine 3x, right? Okay, so now if you combine these two, what you get is 4 minus 1, 3 by 3 is just sine 3x plus sine x, right? And then whatever is remaining here, which is Heaviside function of x minus pi times, if you use the sign properties, it's 1 by 3 sine 3x minus sine x. Okay, So that's your solution for okay. So that's your solution that we need to obtain for 9a. That is the solution of this initial value problem. We have used all these conditions, right? Okay, now let's do 9b. Now 9b is not a different, it is an equation that involves both derivatives and integrals. So it's what is called integral differential equations, and there are also two unknowns, y1 and y2. So it's actually a system of equations, okay, and this also can be handled by Laplace transform. So when you apply Laplace transform, the system of integral differential equations becomes a system of algebraic equations which you can again solve. Okay, so let's apply Laplace transform on to this. So that's okay. So there is no space here anyway. We will start from here and then we can move into the next one. So if you apply Laplace transform throughout, there are two equations. Okay, so you apply Laplace transform here, so you have the derivative, so Laplacian of y1 prime Laplacian of y1 prime plus 2 times Laplacian of y1. So not Laplacian, I don't know why I keep saying that. It's Laplace transform, okay? So Laplace transform of y1 prime plus 2 times Laplace transform of y1 plus 6 times Laplace transform of the integral y2 right, and then 2 times Laplace transform of Heaviside function. But if you are in the positive real line anyway, if the domain is, then this Heaviside function is the constant function 1. Okay, and the second equation is going to give you Laplace transform of y1 prime plus Laplace transform of y2 prime is equal to minus Laplace transform of y2. Okay, and we have the initial condition. So use the formula that we already know about Laplace transforms of y1 prime. So y1 prime will come with p Laplace transform of y1 minus y1 of 0, okay, plus 2 times Laplace transform of y1 plus 6 times Laplace transform of the integral, which is, we have seen in the lectures, what is the Laplace transform of integral, which is nothing but 6 times Laplace transform of the integrand divided by p. Okay, all these are functions of p. Okay, divided by 2 Laplace transform Heaviside function, which is actually the constant function 1, which is 2 over p. Okay, now in the second equation you get the similar thing, p times Laplace transform of y1 minus y1 0 plus p times Laplace transform of y2 minus y2 0, and that is equal to minus Laplace transform of y2. So we use this information that is given to us, that y1 0 is minus 5, y2 0 is 6. So from there we get the first equation becomes p plus right? The first equation becomes p plus 2 of L Laplace transform of y1, okay, and then plus 6 times Laplace transform of y2 over p is equal to 2 over p, and this term y10 is minus 5, so this is plus 5, that becomes minus 5 when you take it the other side, and here you get p times Laplace transform of y1 plus p plus 1 times Laplace transform of y2 is equal to, this is plus 5 and this is minus 6, which is minus 1. On that side it becomes plus 1. Now you have a algebraic equation here. It's algebraic equation. So two unknowns are this, and this, right? These are the two unknowns. So it's a system of equation, you can solve them. If so in the process of solving you might also have to use partial fractions and so on. So I will leave it for you to do it. So if you do that, you should get the solution, the Laplace transform of y1 to be 1 minus p, 12 by 5, 1 by p minus 1, minus 18 by 5, 1 by p plus 4. Okay. Similarly, you also get the other unknown Laplace transform of y2 to be 6 by 5, 1 by p minus 1 plus 24 by 5, 1 by p plus 4. Okay, so now that you have this, now you know what 1 by p is. 1 by p is Laplace transform of 1. This is Laplace transform of e power x. This is Laplace transform of e power minus 4x and so on. So that way you get y1 of x is 1 minus 12 by 5 e power x minus 18 by 5 e power minus 4x. Similarly, you get y2 of x to be 6 by 5 e power x plus 24 by 5 e power minus 4x, and this is the solution that you want for the integral differential equations that we started with, system of equations. So both the unknowns are found. Okay, so that completes problem number 9 here. Okay, now let's do problem number 10. Problem number 10. So we need to find the unknown function y in the integral equation. So these are all integral equations. So there are no derivatives here. All we have are integrals. But the way we have done for the previous exercise, differential equations, like we can also do the same thing for integral equations. You apply Laplace transform to all these equations and then you can find the unknown y. Okay, so let's do 10a. So in 10a, what is given to you is yx plus integral. So what is given to you, the equation given is yx integral 0 to x y tau d tau equal to Heaviside function of So now you take Laplace transform both sides, so you get Laplace transform of y plus in this case is Laplace transform of the integrand over p is equal to Laplace transform of the Heaviside function, so e power minus ap over p, right? This is by second shifting theorem and so on. So e power minus bp over p. Okay, so you have this. So this gives you that Laplace transform of y is p plus 1 over p, so the p gets cancelled, so p plus 1 is what remains, so it's equal to e power minus ap p plus 1 plus e power minus bp p plus 1. Okay, now what are the functions whose transforms are these? So y of x, like we have already used, right? So again the second shifting theorem is going to give you that this is h of x minus a of exponential of minus x minus a, right? Similarly here it's plus h of x minus b exponential of minus x minus b. Okay, so this is the solution that you get. Okay, so this is the solution that you get for 10a. Now let's do 10b. Okay, in 10b you have e power minus x, 10b, which is e power minus x equal to yx plus 2 times cos y d tau. What you should observe here is that, so we again, like before, we have to apply Laplace transform both sides. So there is an integral here, but now it is not just y, there is a product y. But what is this? This, if you know by the definition of convolution that we have defined, this is nothing but cos x convolved with yx, right? So when you apply Laplace transform, what you get is Laplace transform of exponential of minus x, Laplace transform of y plus 2 times Laplace transform of cos convolved with y. In fact, I should not write it like this, right? What I should write here is cos convolved with y, that is a function that we have, right? But and we know what is the Laplace transform of convolution by the convolution theorem. So this is precisely, so what is the Laplace transform of exponential of minus x? Is 1 over p plus 1, right? So it's 1 over p plus 1 equal to Laplacian of y plus it's 2 times Laplacian of cos x into Laplacian of y, right? But you know 1 plus 2 times Laplacian of cos x. What is Laplacian of cos x? It is p by p square plus 1. Okay, this is what you have. So that kind of gives you that Laplacian of y. Just to simplify here, let's do it Laplacian of y is p square plus 2p plus 1 by p square plus 1. This is what we have. So Laplacian of y is p square plus 1, which is this numerator comes as so this denominator comes as numerator, divided by p plus 1, this and this and this, and this is p plus 1 whole square. So you get p plus 1 whole cube. Right? Now if you use your partial fractions, you can see that it's 1 over p plus 1 minus 2 times p plus 1 whole square plus 2 times p plus 1 whole cube. Okay, so you will get this. So once you have this, you can see that y of x is 1 over p plus 1, which is nothing but exponential of minus x, right? And here this is minus 2 times exponential of course, minus x multiplied with a polynomial of degree 1, which is x, plus 2 polynomial of degree 2 exponential of minus x, and this is exponential of minus x, right? 1 minus 2x plus 2x square. Okay, so with this, so this is what we'll get. There's some error with my solution. I mean, did we do everything correct? Okay, so that's something to do with partial fractions. If at all there is a problem only with partial fractions. Please check whether this 2 is coming or not. Okay, if this 2 is not coming or not coming, then this 2 is not there. Okay, so in that case, this 2 won't be there. In that case, it matches with this with my solution that we computed, which is x minus 1 whole square. Okay, so please, yeah, I think probably there will not be a 2 here. Okay, so that's fine. So that's where we have solved. So please verify this. Either this is the solution with the 2, or this is the solution, one of them. That's, I leave it for you to check and verify an exercise. So that's about 10b. Now let's do 10c. Okay, 10c is 3 sine 2x is equal to y of x plus integral 0 to x minus tau y of tau d tau d tau. Okay, now you can see here again this term here, everything else is fine. This term here is nothing but the convolution of the function x convolved with y. This is convolution of that function. So if we apply Laplace transform, it's 3 Laplace transform on 3 sine 2x, Laplace of y, and it's Laplace of x, this, which by the formula, so sine 2x is something which we know, it's 2 by 2, so it's 6 by p square plus 4, and that's equal to Laplace transform of y, and this is Laplace transform of x into Laplace transform of y, and that is L of y 1 plus Laplace transform of x is 1 over p square. Okay, so that's going to give you Laplace transform of y is equal to, so here it actually becomes Laplace transform of y p square plus 1 by p square, so it becomes 6p square by p square plus 4 and p square plus 1. Okay, now you apply partial fractions, use partial fractions to compute this, so then you should get, this is 8 of p square plus 4 minus 2 times p square plus 1. Now this is something which we know what is Laplace, so y of x is precisely, right, so p square plus 2 square, so that gives you 2 by 2 square, so 2, so it's 4, so 4 sine 2x, okay, minus 2 times sine x, okay, and that's your solution. Okay, so this is 10C. This problem is also solved. All these are integral equations and we have solved them using Laplace transform. So that's the final solution for 10C. Okay, so with this we have completed this assignment and also probably more or less most of this thing in the course. So everything is fine. Please, only this thing, this calculation I not done for you, so I'm unable to check now. I don't want to do it and check it now, but it's something easy to verify. Use partial fractions here, write it down, whatever comes out is a solution. When I did it last time, it turned out to be this, but please verify if it's this or this, whichever. Okay, so with this we will stop. Thanks a lot. Bye.